Alrighty guys, let's go ahead and get started with our UCM notes, part 2. And these notes are going to focus on objects that are on the Earth. So before we dive in though, let's go ahead and recall what we already know about UCM. And again, UCM just means uniform circular motion. What is UCM? Well, like we said, it's uniform circular motion. So that means that objects that move in a circular path exhibit uniform circular motion. And let's talk about what remains constant in this uniform circular motion. So as these objects are moving around in a circle, what things do we know are not going to change? Well, the radius of that circle is not going to change. It's going to have the same radius the entire time it moves or undergoes uniform circular motion. It's also going to have the same speed. And we remember that speed is really just the magnitude of velocity. And magnitude meaning the absolute value, right? Next, we have our acceleration, and the acceleration also is not changing. Another key thing to note, though, is that our acceleration is not zero. Our acceleration is some value, but it's a value that is constant. And lastly, we have some sort of centripetal force. We need to know that that centripetal force is not changing either. It's going to remain constant. The centripetal force is any force that's going to point towards the center of its orbit. So we'll talk about a few examples in a sec as well, but just know that when an object is undergoing uniform circular motion, whatever force is pointed towards the center of its motion or of its circular orbit is going to be our centripetal force. All right, I know some of you guys are thinking to yourselves, but Mr. Weiss, how can we have acceleration and constant speed? That just doesn't make sense. Isn't acceleration the change in speed or something? Well, acceleration isn't the change in speed, it's the change in velocity over time. And let's go back to what we said about that. So something important to remember is that velocity is a vector. And what's a vector? Well, a vector is something that has magnitude and direction. So the key takeaway here is that velocity has magnitude, which is a size associated with it, how big, and also direction, which tells us what way it points. Centripetal acceleration, the one that we're talking about for uniform circular motion, only changes the direction of that velocity. So because we're moving in a circle, we're constantly changing our direction. But the size or the magnitude of that velocity is never changing. It is staying the same the entire time. And like we said, since speed is the magnitude of velocity, speed does not change. It will remain constant in uniform circular motion. So what's the deal with this whole centripetal force thing? Well, let's talk about this diagram a little bit. And we know that anytime an object is exhibiting uniform circular motion, it must have a force that's acting on it towards the center of its orbit. And over here in our diagram, we can see that. Here's our object, our red blob that's going around in a circle. And I see that there's a centripetal acceleration pointed towards the middle. The same direction that that centripetal acceleration is pointing is going to be our centripetal force. And this force is what's keeping that object from flying off in a straight line. So let's think about inertia really quick. And if we remember, inertia, right, is an object's tendency to keep doing whatever it's doing. Basically, in this case, it's telling us that objects in motion will stay in motion. This is an important concept, and we'll come back to it a little bit later in the notes on how inertia is going to play a role in our centripetal force and just uniform circular motion in general. But let's just wrap up this slide saying that centripetal force can be any force that points towards the center of an object's orbit. And on the next slide, we're going to talk about what types of forces it could be, just a few examples. Before we move on to the next slide, though, notice how in this simulation, we have r, and r is constant. That value is not getting bigger. Notice that we have centripetal acceleration, which is also constant. That length of that arrow is staying the same size. And then notice that we have V. V stands for velocity, but we notice that the arrow length is staying the same. But what do we notice about the direction of that arrow? Well, that direction is changing. It depends where we are on this orbit, but the direction of velocity we can see is always changing. And if we look really closely, we notice that it's perpendicular to our centripetal acceleration and also tangent to our orbit. Now let's talk about a few examples of centripetal force. So the first one we're going to talk about is force gravity. We've already talked about this before, and we know that force gravity is relevant when it comes to planets, satellites, and just orbiting around each other. Here's just a little GIF showing that, right? We have the Earth and we have these satellites orbiting around it. These satellites are exhibiting uniform circular motion, which means that they're feeling a centripetal force towards the center of the Earth. And again, that centripetal force would be force gravity. They are feeling a centripetal acceleration towards the center of the Earth, and they are moving with a velocity that is tangent to their orbit. All right. And the speed is constant because it's uniform circular motion, but the direction is always changing. And we can see that the satellite is changing directions. Now let's take a look at force friction as a centripetal force. Well, an example of that could be a merry-go-round or possibly cars turning. And over here, we have a kid on a merry-go-round. We know that force friction is what's holding them because if we look at their feet are stuck to the merry-go-round. If we were to remove the friction of the merry-go-round, what would happen? Well, this kid would go flying off the merry-go-round, which just affirms the fact that friction is the centripetal force in this case. Also, for a car, here's a car going around a circle. This is really relevant for those of you that live in Brookfield, right? 8 corners. And what is holding the car to the ground? Well, it's friction. If this was snowy or something, or they hit a patch of ice or whatnot, the car would end up sliding off, right? What direction would the car move in? Well, that's a great question. And the direction that the car would move would be tangent to its orbit. So for instance, if the car hit a huge block of ice, like right here, the car would end up moving in the same direction, and that would just be perfectly straight down. The next force I want to talk about is tension, and an example of that could be swinging something with a rope above your head. In this instance, we have a guy swinging a weight around. All right, the centripetal force, or the force that is pointed towards the center that is preventing this mass from flying off, is force tension. Because if we were to cut that string, this weight would just go flying off. And again, it would go flying off tangent to its orbit on when it was cut. So now let's just quickly recap everything we talked about. Velocity is tangent to the orbit. We can see that in our diagram to the left. And the reason we say tangent to the orbit is because velocity is always changing. And at different points in time, the velocity is going to point different directions. So like right here, the velocity points up. But if we go over here, the velocity is pointing down. So we need to make sure that when we're talking about it, it's in reference to where it is in the orbit. And again, this just shows us what direction our object would move if that centripetal force were to disappear. Our object is moving, though, in that direction while it's around the circle. It's just constantly changing directions, though, because of the centripetal acceleration and the centripetal force, which keeps pulling on it. Centripetal force, like we mentioned, will always point towards the center. That's why it's called the centripetal force, center pointing force. Well, we know that net force equals ma. And we know that for centripetal force, that's the only force. So our net force is really centripetal force, which means that centripetal force equals ma. And we know that objects that are experiencing acceleration are going to accelerate in the direction of the net force. Therefore, the centripetal acceleration is going to point towards the center because our centripetal force always points towards the center.